Good afternoon. I welcome you to our chemistry class today. And in our lesson today, our discussion will be on the industrial manufacture of nitric 5 acid. And this compound, the substance nitric 5 acid, is used in industry for very many uses. That is why there is need for it to be produced in large scale. Some of the uses that I have highlighted here, just a few of them: manufacture of fertilizers like ammonium nitrate, manufacture of explosives like trinitrotoluene. This is a form of explosives. Alongside many uses of explosives, you have like constructions of roadworks, for other forms of constructions of buildings, and other forms of constructions, especially for civil engineering. Manufacture of dyes and drugs is also another use. Purification of metals like silver and gold. To purify such metals, you require also nitric 5 acid. And finally, aging designs on some metals. If you want to create some designs, some drawings, some patterns on metals, nitric acid actually is highly used for such purposes. And for this few very important uses is now the reason why nitric acid is a major requirement in some of these industries. Now, the manufacture of this nitric acid relies majorly on the catalytic oxidation of ammonia. Now, catalytic oxidation of ammonia will result in the formation. You look at the steps. In the beginning, formation of nitrogen 2 oxide. Then nitrogen 2 oxide is oxidized to nitrogen 4 oxide. Nitrogen 4 oxide thereafter will be converted to nitric 5 acid and nitric 3 acids. 2 acids are actually formed in the process, and the whole of that process will follow some sort of a flow diagrams, where you also have other raw materials which will be included in some of the steps which you are going to consider. However, the main raw materials, we have ammonia, we have air, and also water. Ammonia can be sourced from the Haber process. This one can be sourced from the Haber process. Then air is present in the environment. Particularly for the air, we require oxygen. And then for the water, it's actually also a major raw material, and that is an indication that every time a nitric 5 acid plant is to be established, it must be close to a water source. Some of the notes that I wanted us to have in our discussion, because we'll be using them from time to time. We have ammonia, we have nitrogen 2 oxide. These are the chemical formula for ammonia, for nitrogen 2 oxide, nitrogen 4 oxide, nitric 5 acid, and finally nitric 3 acids. These 2 acids are formed at close to the end of this process, and therefore this nitric 3 acid must be oxidized to form nitric 5 acid. Now, our focus on the flow chart, which is the flow diagram for the summary of the major steps of this process, is that you will begin with the 2 raw materials, ammonia and also air, into the purifier. The purifier removes the impurities, dust particles and others. And the reason why we need, or there is need for the removal of the impurities, is to prevent the impurities from poisoning the catalyst. To poison the catalyst is to lower the efficiency, to make the catalyst to be less efficient. And therefore, there is need for the impurities to be removed. And one major way of removing the impurities, especially the dust particles, is by the process of electrostatic precipitation. The ammonia and air exiting the purifier into the compressor will be at a very high pressure of around 9 atmospheres. So this mixture of air and ammonia will be compressed to pressures of about 9 atmospheres. And out of this compressor exiting, the mixture of the air and ammonia exiting this will be at this pressure, and then into the heat exchanger. So heat exchanger is where you will have temperatures of about 230 to 290 degrees Celsius at the heat exchanger. So these are very high temperatures. So out of the heat exchanger, you expect the mixture of ammonia and air to be at very high pressure and also to be at the temperatures as indicated, 230 to around 290. Now, this mixture of air and ammonia at the temperature and pressure indicated will actually go into the catalytic chamber, where now you have the catalyst. And the catalyst which is required there is what we refer to as the platinum rhodium catalyst, which will be used here. And the catalyst will actually will enable the reaction between ammonia and actually air, and we have that equation indicated here. So you have ammonia reacting with oxygen in air in presence of that catalyst to produce nitrogen 2 oxide and also and water, nitrogen 2 oxide and water. So here you have this is where you now have the catalyst as indicated. This is the catalytic oxidation of ammonia to produce nitrogen 2 oxide and also and water. Now, after this, the catalytic chamber, now you have the nitrogen 2 oxide air and also partly unreacted ammonia back into the heat exchanger, and then now from the heat exchanger down to the reaction chamber. So you have the cool nitrogen 2 oxide and air. The unreacted ammonia will also react with this heat exchanger after being recycled back, then into the reaction chamber. So at the reaction chamber is where now you have the reaction between this nitrogen 2 oxide, purified air, or actually with the air that accompanies it in this reaction chamber. This now you have the conversion of nitrogen 2 oxide to nitrogen 4 oxide, and that equation is here. So nitrogen 2 oxide with oxygen either from the purified air or from this air to give you nitrogen 4 oxide. That's where you have the nitrogen 4 oxide, you have air, and also the unreacted nitrogen 2 oxide. Now, this mixture enters this absorption tower where this mixture comes in contact with warm water. So the mixture of nitrogen 4 oxide, air, and the reacted nitrogen 2 is passed into the absorption tower, very important, absorption tower, against a downward flow of hot water. There is hot or warm water there. The nitrogen 4 oxide combined with water to form nitric 5 acid and also nitric 3 acid as indicated. So you have this one, you have nitric 5 acid and also nitric 3 acid being formed. And this is the equation for that reaction. We balance this, so we have nitrogen 4 oxide, water, to give you, we have 2 there, so that it is now balanced. So nitrogen 4 oxide and water to give you nitric 5 acid and nitric 3 acid. So the 2 acids are formed, and the nitric 3 acid formed is then oxidized. This is not the actual acid that we want. It has to be oxidized to form nitric 5 acid by excess air, which is still there. Then from here, the absorption tower, so you have your 65% nitric acid, then the unreacted nitrogen 2 oxide and also air is recycled back into the compressor, and the whole process again takes place. So something we can also reiterate is that at the purifier, the dust particles are removed, which may otherwise poison the catalyst. At the compressor, this is where you have pressure of about 9 atmospheres. The heat exchanger, temperatures around 213 degrees Celsius. And then at the catalytic chamber is now where you have the temperature of the mixture, that is the ammonia and air, is raised to around 900 degrees Celsius, and then it is passed over platinum rhodium catalyst. Then you have the equations as indicated. The hot gaseous products are further cooled in the heat exchanger. So the moment you have this mixture getting back into the heat exchanger, then there is cooling taking place, and then that's why you have cool nitrogen, 2 oxide and air exiting that heat exchanger. Then thereafter, from the reaction chamber, nitrogen 2 combines with oxygen in air to form nitrogen 4, and then the nitrogen 4 at the absorption tower combines with warm water to form nitric 3 acid and nitric 5 acid. The nitric 3 acid is oxidized by excess air to form nitric 5 acid. Whatever did not react is taken back into the compressor, and the whole process starts once again. So that is the flow diagram that describes the entire process for the industrial manufacture of nitric 5 acid. That marks the end of our discussion.